that's around the rod supposed to provide a different index. Both glass, but they're a different index the way they're made.
So the beam is not being reflected after going to the different.
No, I exaggerated it here by going through here, but in fact it happens very quickly. So it looks as though it's coming off the surface, but without this, it wouldn't, you know. Or you could even argue, even if you didn't have glass around it, if there was just air around it, air has a different index than glass, and so therefore again you will get a certain amount of refraction and therefore reflection. But the problem with air, of course, is, you know, it's not as good as something solid around it. That's the difference.
So when is it going to be when we apply light, it goes through the rod in outer space?
Well, yes. One thing that it will depend on is the frequency of the light, which I haven't mentioned much about here. The frequency of the light can be critical. At certain frequencies, the light will be reflected like this, and therefore will stay within the rod. But you could choose different frequencies which cause the light to go straight through. It might get refracted a bit, like that, but then will go through to the air or through to the outer surface, and you'll lose the light.
Lower frequency?
Depends on the frequency. Yeah. Higher frequency or lower frequency. Lower frequency are usually just like the ionosphere in that example. But higher frequencies can also cause it. So the frequency can be critical as to whether your light is maintained within the rod. And of course different refractive indexes would be used for different frequencies. So a particular optical fiber cable would be designed to operate at light at a certain frequency. Now this becomes a bit of a problem because when you want light to be at one frequency, the light source here, this is the light source, the origin, as it were, of the light, okay, has to produce light at one frequency and one frequency only, and it has certain polarization, what we call coherent light. And the only device that can do that is a laser.
So that's not normal light?
Not normal light. Well, laser's normal light. It's very...
Straight beam.
Yes, it produces what they call a coherent beam. One frequency, one polarization, either horizontal or vertical. Okay. Called coherent light. And a laser would be used, not a high power laser, we're not talking about something very high power, to produce the light necessary to be totally refracted. Yes, yes, essentially. That's right. For efficient propagation down the cable.
Laser is always red?
No, not necessarily. I think infrared is a common frequency, but other frequencies can be used. You've got one there, have you? It would be maintained and it would follow the bends of the cable.
Can we use it in telecommunication?
Yes, it is used actually in that. Yes. For if you remember when we talked about the different bands of frequencies in the RF range, we spoke about VHF and UHF and SHF. Remember these? These are in megahertz. SHF 3 gigahertz to 30 gigahertz and so on. Now, one advantage of going to these higher and higher frequency bands is you have more space in the spectrum to fit more channels, don't you?
Yes, yes.
The bandwidth increases. And remember, right at the beginning of this course, bandwidth is proportional to the rate of flow of information.
Yes, yes.
Right. Well, if we make a big jump from here, and I think it's in your diagrams, if you go to light waves, What sort of frequencies are we talking about there? In the visible light wave spectrum.
More than ultra.
Yes, is it in, does it give you the figures there? I'm not sure if it gives you figures there.
Extremely high frequency.
Extremely.
No, does it go to light waves? It might not go to light waves.
I think 1,000 giga. 1,000 giga.
It's something mean 10 to the power.
Okay.
Extremely high frequency.
10 to the power 8.
Giga to 300.
No, light waves are obviously not in there. Hertz.
But,
Now,
but there is here in the 1,000 gigahertz.
100 giga to 1,000 giga.
1,000 gigahertz.
yeah, but it's, these
This
are...
last one extreme.
Yeah, so they're way, way higher than that. Way higher than that. So we're talking about very, very high frequencies indeed. Okay, now this means that if we can use light waves instead of radio waves to transmit our signals, we have a much, much wider bandwidth.
More information.
More information. This is the secret of why we would use fiber optics to transmit information rather than using copper cabling or even wireless or even radio, because the standard radio we're limited to SHF, perhaps microwaves, and then only a short distance, point to point. If you want long distance, you need cables so they can go around the curvature of the Earth, right? Long distance cables.
Yes.
But copper cables, unfortunately, don't have a very wide bandwidth. They're limited. Right? And so therefore, much better if we can lay our cables using these fiber cables, fiber optic cables.
They won't trust.
Yes, oh, there's a lot of advantages. First of all, of course, being glass,
Very
they should last longer.
Very expensive.
Well, it certainly was more expensive than copper. It's becoming cheaper and cheaper, though, as more and more of the stuff is manufactured. So expense is becoming less of a problem.
Technology.
Yes, as technology changes, this thing is now becoming cheaper than copper. Okay? So expense is now no longer a problem, as it used to be in the old days. Right?
Copper is so expensive.
Yeah, copper is now the expensive thing.
Expensive.
It used to be the copper was cheap and and these things would be very expensive, but now it's the other way around. So we can see a big advantage in using this. I haven't spoken yet exactly how we use it, but just by looking at the physics of it, we've got a much wider bandwidth available to transmit information. Now fiber would be used probably to connect communication systems between major cities in a country. Right? In any country now, doesn't matter where you go, if the telephone people are up to date, they will be putting fiber connections between their major cities. Now, a single fiber cable can hold many thousands of telephone channels. Probably they would use TDM, time division multiplexing, using PCM. But we'll talk about that when you do data comms. But we can afford to get thousands of telephone channels down a fiber cable because we're using such a high frequency in the light wave spectrum instead of the radio wave spectrum.
The copper what the frequency is.
Copper, you're limited to audio frequencies or just a little above them. That's what you're limited to.
A couple of months ago, there was this new technology coming to the market. It was the maximum number of telephones or calls can be done with 30,000 or something.
What technology was it? Was it this sort of technology? Or?
Something like
Mhm.
this, yeah. And it was a big jump to go from.
I'll tell you what it might be.
It's 20 times.
Could be. I'll tell you what it could be, if it's what I'm thinking. Remember I said that the standard cable here uses infrared?
Yeah.
Well, what if you could use ultraviolet or something in the... Now, the problem is developing these lasers. These lasers here are usually made from semiconductors, laser diodes they call them. Quite expensive, you know, but these are the transmitters that are used. You just connect a voltage to them, just like that, and it shines a light. take the voltage off, the light stops. So they send the signal that way. But for many, many years, they couldn't design lasers to radiate blue light. Couldn't do it. They tried all sorts of things. And when they did eventually manage to do it, it was very, very expensive, using special expensive materials. Now, and I think this might be the change that's made, they've now found a cheaper way to design a laser using semiconductors to radiate blue light, right? Maybe even ultraviolet light. Now, ultraviolet light is a much higher frequency than infrared, even in the light wave spectrum. So, again, this will give you even greater channel width, and it could be that. I'm not saying it is, but it could be that I've heard about.
I heard about it, but I wasn't sure what it exactly. But
No,
it was the biggest jump.
yes,
And
yes,
it's not yet in the market.
probably not.
It's now understood.
Yes, I had heard something like that, and but anyway, you can imagine the big fibre. Now remember, these fibres that I've drawn across, they're no thicker than a hair. You know, they're very, very thin, and they're surrounded with insulation, a little bit like a copper wire, only the insulation is to just protect the glass from being broken. All right, the insulation is quite thick compared to the thin glass fibre, to give it plenty of sponge, to give it plenty of protection against.
And that's at last put out two.
Oh, sometimes several. Yes, sorry, you're right. This is 2-in-1. I've just shown it as a single thing. It's like this. And then, of course, when they're laying cables using fibre, they would use many of these. There would be many fibres, like as individual channels. You know, many hundreds of these perhaps in one bundle to go between cities. So the bandwidth is quite enormous, quite large, that they've now got between major cities within the country. And this is what we call the backbone of your telephone system, which carries all your trunk lines between cities. Now, of course, one disadvantage is, well, it's not a disadvantage, but you can see that technologically there's going to be a problem here to change your telephone channels, your thousands of telephone channels, into a suitable signal for the laser. Well, it's outside the scope of this course to say how that's done, but it will be a type of TDM, time division multiplexing, which we will talk about when we do data comms. Now, at the receiving end, what you need here is another device, and again, it's made from semiconductor, it could be type of
I
diode.
use kind of resistor.
You can do, but that would be very slow. They use faster things called photodiodes.
Photodiode.
Yeah. Light does the opposite of this. This produces light, this changes light into electricity, like a sensor. Right? Now, of course, again, between two cities, you cannot just use one length of fibre. You've got to have repeaters periodically. Because, again, it's not 100% perfect. You are going to get losses of light.
So write the advantage and the disadvantage about the fiber.
I will be writing all these down later, yeah. You are going to get some losses. No, a lot less. You can get a much greater distance using fibre before you need to use a repeater than you would with copper. But it's not infinite. I mean, there is a limit.
The signal gets weaker, the light.
Yes, the light gets weaker and weaker. So you do need to regenerate.
For long distance, is there any noise?
There will be, as the light gets weaker, although it seems quite a perfect little situation that I said here, nothing's perfect, of course, a little bit of light will be lost. You can't get everything.
This information loss.
Yeah, and therefore it's like the signal getting weaker and weaker as it goes along. A lot greater length than you would have with copper, but you still need to have repeaters. Basically, a repeater would be a photodiode, right, creating, and then a little amplifier, and then another laser for the next section of the, you see, regenerating your signal. It'll all be digital signals by then, by the way. These are all digital signals, not analog, so they can be regenerated. And when you make your long-distance telephone call now to another city, say to Riyadh, you're actually going to be using part of your call will be transmitted over these laser links, these optical fiber links. Well, there's a problem. It used to be quite a big problem. If ever this got cut or damaged, or you needed to connect two together, it was quite a specialised piece of gear you needed and a little bit of expertise. Now it's become a bit easier. The manufacturers have made it a little bit easier for the average technician, with a minimum amount of training, to be able to join two. Obviously, you don't use solder. Special. Yeah, you need special gear to be able to join your, because it's got to be a perfect join, you see. You've got to perfectly join these to the next piece of fibre. If you don't, you're going to get losses here. Light is going to escape or get attenuated. Well, yes, but that might not always be possible. Because you could be talking about several kilometres length. Yes. Oh, well, obviously if a full cable's cut, I mean with several strands, then it's best to replace the whole thing, yes. They can do, but it used to be quite a specialised job. I think it's becoming a bit easier now. This is now becoming more of a standard technology. Yeah. Well, it was a few years ago they were saying that eventually they want a fibre connection into everybody's home. And if they had that, then you would have all your TV, your telephone, your everything, and the internet, everything in the one fibre. Yes, quite flexible. I wish I had some here. I'm going to try and find some, show you, but it's no thicker than, say, this, right? It's like this, exactly the same. You can do that with it, right? But most of this is insulation. It's only the very middle of it is the actual glass. So it's very flexible, just like ordinary. You can do that with it, no problem, although you shouldn't. But I mean, you can, you know. Quite flexible, yes. Quite flexible indeed. And small like this. That would be a typical thickness of a fibre that would be running between Jeddah and Riyadh.
No, it's exists between
All major cities will have this. Yes. Yeah, this is it. This is about typical thickness, and that most of that is insulation. Inside there, you've got the actual glass. That's why it's so very flexible, because the glass is very, very thin.
Flexible glasses.
Yeah, it's very flexible. This is not a fibre, but it's the typical thickness of fibre. Yeah, you can break it, yes, that's right. You can break it. That's right. You've got to be a little bit, I mean, you wouldn't normally do that. It's capable of doing that, but...
Long distance. This is advantage, Mr.
These are the advantages.
Make a meeting with you.
Who's going to be at the meeting?
Yeah.
I'm not sure everybody, but Atif will be one of the guys.
And
Actually, Salah Khamash won't be there because he's busy doing something else, so I'll be there in place of him. There are several other guys. I forget the names now of everybody. Yeah, but I don't know. I'm not sure whether he'll be there or not. I don't know.
The schedule.
Is there something? By the way, if there's anything particularly you want me to bring up at the meeting, I will do. If there's something you want me to say, or you know.
Yeah. To give us.
The idea of the meeting is actually to decide
نرفع قريت شوية. هذا اللي بدي أكلم عليه. مو في أنسى تدري أنسى.
two different types of copper cabling.
اشتركوا بعض الاثنين. سيفتي ما في خالد؟
There's some points of safety, and also one or two points about different types of copper cabling. We're not going to go too deeply into this because that's a different course, but you should have an idea about these three types of cables that I've mentioned on the board here. Coax and twisted pair, both shielded and unshielded. All right. First of all, you all know what coax cable is. You've seen this? This is where you have a center conductor with an outer insulation around the conductor, and then around there you have what appears like a shielding, a copper braided shielding.
Use it for the receiver and satellites.
That's, well, yes, indeed, you can use it for any communication, and then around there you have a plastic coat. TV connections, for example, you're probably familiar with that at home. TV connections would have this sort of cabling. But coax cabling used to be used for channels, trunk channels between cities and telephone systems, before we used fibre. Remember yesterday we said that now fibre optics. Fibre are the things we use. But before fibre, coax cable was the main way of transporting a large number of telephone channels between cities. Okay? And the reason is this has quite a wide bandwidth.
I thought the reason they use it for the TV.
Yes, indeed it is. And it's the reason why they can use it with multiplexing to accommodate a lot of telephone channels if necessary. Not as high, of course, as fibre. Fibre gives you the maximum number of wide bandwidth. That's why my W's a bit crazy. Wide bandwidth. Now, exactly what bandwidth depends on how the coax cable is made, but it's wider than any of the other conductors we're going to talk about here. But, of course, it's not going to be as wide as fibre. Fibre gives you the maximum bandwidth, as far as cabling is concerned, anyway. Now, usually, this outer conductor is grounded. I'll make a little point here.
That's the reason.
It is acting like a shield, electromagnetic shield around the center conductor. You know what I mean by a shield?
Yes.
Particularly in terms of electronics, something that prevents something from passing, to shield something from somewhere else. So, in this case, the electromagnetic currents that flow in the coil, in the cable, obviously they're going to produce electric and magnetic fields. Well, this shielding prevents that field from radiating out and interfering, and also prevents noise from getting in. The result is it gives us a much wider bandwidth than using a straight copper wire. Okay. Now, the next type of conductor here is shielded twisted pair. The shielded twisted pair is very similar to the coax, except it uses two conductors which are twisted together, and then around there we have some shielding, very similar to this sort of shielding, and then of course an insulation. The bandwidth of this is narrower than the coax cable, so it's a narrower bandwidth than the coax cable. The advantage of it mainly is it's more flexible than the coax. Much more flexible than the coax.
To have, I think, twisted pair, 2 pair or 4 pair.
Yes, yeah, that's very true. Usually when they make this twisted pair, the IBM standard, they use 2 of these twisted pairs, and they also use some extra conductors to carry some extra signaling in the same thick cable. We have some examples of twisted pair upstairs which I can show you, but I don't have any here. I don't think there's anything here of twisted, not of the shielded twisted pair anyway. No, they use unshielded. This is becoming less popular now. This is an old IBM standard. It's not used for older types of local area networks. The coax cable can also be used for local area networks, for LANs, as well as long distance communication. Probably the next most common type of cabling is the unshielded twisted pair. And of course this is your standard telephone cabling, as well as nowadays the LAN cabling. Okay, this is the unshielded twisted pair. The most flexible of them all. Much easier when you're wiring a building, something like that, for a network, to use this. And this is the most common. It has the narrowest bandwidth, but it's still sufficient for a lot of uses. Okay, so this would be just basically a pair of conductors which are twisted together. Why do they twist these conductors together, do you think? And of course you've got a plastic coating.
Because each one
Like bear.
It is a pair, but why do they twist them round? What was the advantage
they
of
make
twisting?
confused. They make this one. The other bit.
Okay.
Because there is a fixed color like the white.
Well, yes, but I mean, why they actually twist them around together, right? You know, like that.
No, that is together with.
No, it's not to pair them. There is a technical reason why. Yes, to minimise what? Well, yes, and interference. The fact is, of course, that each of these represents a circuit, doesn't it? Two wires represents a circuit, goes to the whatever it's going to here, and then comes back. So there's a current flow through each of these cables. Now it's important to realise that the current in one cable is equal to the current in the other for a pair. So the magnetic field generated by one current will be cancelled, because this current's in the opposite direction, by the magnetic field in the other. By twisting them around, right, you make sure that the magnetic field from one and the magnetic field from the other cancel one another, so you don't get any interference. And similarly, any noise coming from outside is cancelled within the twisted pair. So that's the reason why they twist them around.
Only they do this twisting with a telephone line.
Telephone and anything that uses, for instance, this is not a telephone line, this is a LAN cable. It goes to our local area network in the building. It's not for telephones, but it's similar cabling. So it's not just for telephones. But yes, telephones is an example. Your local loop, for example, coming from your telephone exchange to your telephone will be twisted pair.
Can you say the reason, please, again?
For twisting,
Yes.
I will will do. Just 1 minute. Let me just put the little note down here. This little bottom piece here explains why we twist the cables together. Because the current in each wire is the same, but flowing in opposite directions to conform the circuit. Usually the wires you twist together form a complete circuit. So the current flow in each direction is the same, hence the magnetic field produced will cancel. And it's the same with magnetic fields from the outside. They'll cancel in the cabling, so you won't get as much noise, and you can afford a wider bandwidth of signal. This is the reason why we twist the cabling together. And indeed, for both the shielded and unshielded, you have twisted cabling. An advantage of using unshielded, of course, is it's very flexible. Probably, yeah, that's right, indeed. I can make that point, I suppose. Cheaper than shielded and cheaper than coax, for sure. Coax is not that flexible. It will, of course, bend, but it's not as flexible as this stuff, which is easier to. You know, if you had a coax cable going to your telephones, it would be not as flexible, it wouldn't be as convenient to move your telephone around, things like that. Of course, it's more expensive. These are the most common types of copper connections you're going to get and you're going to deal with. Radio guys will be dealing a lot with coax cable, of course. Data guys mainly with the twisted pair, but of course both of them are going to be used in both cases. So you must be familiar with them. Every use, I mean, you wouldn't use it for telephones.
No, between the twist.
Between these two, well, this is going to be better, but we don't have any here. But if I showed you, it's quite thick stuff because usually it's made with 2 or 3 twisted pairs in the one shielding because it's expensive and it's bulky. So it's not as flexible, you see. Whereas this stuff, this is unshielded twisted pair. Now you can get 4-wire and 2-wire, of course, you know, as you might know. But it's much more flexible, you see. Easier to connect to telephones and things like that.
This without the child, the kind, and child.
Shield.
Not interference.
That's right. Even without the shield here, you cut down on the noise and you get a wider bandwidth than you would without the twisting. But the shield protects the twisted pair even better, gives you even greater noise immunity and a wider bandwidth. Whereas this, of course, the main reason for using unshielded is mainly it's cheaper and it's more flexible, so it's ideal for local loop telephone connections and also for LANs installation of local area networks could use unshielded twisted pair, just like this here. And this is precisely what we use in the building here. Between the hubs, on each floor here we have a hub. Behind that door there, there's a hub. It's locked, I can't show you now.
What about use of shield?
Shielded. Actually, this is not so popular. It used to be popular. It's an IBM standard.
The same uses.
Yeah, same uses really. Exactly the same. Yeah, it's an old IBM standard. We have some upstairs. When you were doing that little test, you know, on the computer, they were all connected. You wouldn't have noticed, but there's actually using shielded twisted pair there. It was quite a thick cable. You know, not as flexible, not as. I don't think you see much of this now on a day-to-day use as the older systems.
The thickest cable is the coax cable.
Probably. There are different thicknesses of coax too, depending on its use. There's some quite thick coax cable, which is very efficient and has a wider bandwidth. And there's thinner coax cable, which is a little more flexible, thin coax, but not quite as wide bandwidth.
The shield.
Yes, they're both about the same in terms of flexibility. But this is probably the most common you will see, the unshielded twisted pairs, but it's common. It has the narrowest bandwidth, but it's sufficient for most of the uses we would need to use it for. The cheapest and the most flexible. In every case, to protect them. And of course, it doesn't matter which one of these we take, even the very best of the coax cable, although I've got here wide bandwidth, remember it's not going to be anywhere near as wide as fibre. That's your best. These coax cables used to be used between intercity connections for telephone trunk lines, which could handle hundreds of telephone calls per cable. But now they're being replaced with fibre, which can handle thousands of telephone calls per cable. So the fibres more or less taken over. This used to be used. The coax used to be the standard for trunk connections between cities.
What was used for TV broadcast?
TV? Yes, your TV connection to your antenna is usually coax, isn't it? That's right. TV is a wider bandwidth than a telephone, so twisted pair wouldn't be very good for TV, perhaps. There are different qualities of coax cable. I mean, you know, you could split these three categories into subcategories and even go even deeper than that, but it's not necessary here to do that. Cabling that we've learnt about. If you get any questions in an examination on cabling, particularly T2, T3 stuff, it's not going to involve much more than what I've told you here. Very simple, very basic stuff.
A2 or 3.
Sorry?
Safety.
Safety.
A2 3.
Oh, sorry. Okay. Did this yesterday, actually, didn't I?
Yeah, one BC.
Okay, then 1 BC. Or even better, you can do 1. The safety is concerned. It's usually, if you get any questions on safety, they're going to 3 main areas, 3 main concerns here. One is fire, the other is high voltage and electrical safety, and the other is physical. For example, wearing eye protection or using some sort of eye shield if you're dealing with. Actually, you're supposed to do that when you're soldering, because of you can get when you're soldering, particularly from the flux, it can splatter sometimes and squirt some solder out. But this sort of thing. As far as the fire is concerned, basically the use of fire extinguishers is the question they'll ask. If they're going to ask you any question at all, if you consider the different types of fire extinguisher that you're going to be dealing with, There's water, of course.
Class A and class B.
That's right. There's different classes of fire extinguisher. Powder or gas.
Yes.
If you were to, I mean, a simple question, and this is probably the most common question. If you had to put out a fire that was caused by an electrical short,
Powder.
لا gas.
Powder.
well, the question is going to be simpler than that. Would you use water?
No.
No, that's right. That's it. I mean, you're not going to get anything more involved than
Which
that.
choice is that? What did you get?
Oh, they'd make it very obvious, I
بس
think.
powder كهرباء.
They'd probably say, what would you not use? And water would be given as an option.
فوم
What is phone?
هالون
At Hallam.
Yeah, the gas, the Holland system is where you have a large container of gas, usually a circular container in the corner of a room somewhere. Right, yeah, it can be. And I'm not sure, they used to use it here in the mainframe room, but I'm not sure if they still use that, the Halon. Basically, in the event of a fire, it fills the whole room with.
I think
With gas.
that Hallam system it has a automatic system to operate.
It is, it's automatic. It's not something you normally set off by hand. When it detects smoke or heat,
Just any flame.
and then it's supposed to fill the room within a fraction of a second, actually, with
The
gas.
sensor, I think, sensor.
Yes, they found that it can be dangerous. They kept telling us it was all right to be in the room.
Be the room closed also.
Yes, but I certainly wouldn't. I mean, just the sound of it alone could definitely, let alone the gas itself. I mean, if it's going to put out a fire, surely it must affect your breathing, mustn't it? You know, that's the whole objective. So they've actually got a newer type of system now where, and again, I'm not sure how it works, a different type of gas which is safer than Helen for human safety.
That one it is not effective. We use it in our tracking system.
You use it in the trunking system, okay. It has been replaced, I know that. When they first built this building, we went around and they demonstrated the Helen to us. It cost them $2,000 to recharge it, but it was a part of their installation procedure, so we all accumulated in the NCC department. If you've been to NCC, there's a big window around separating the communications side from the mainframe, and they were going to let off the Helen in the mainframe area, so we all stood on one side and they let
Very,
off the
very
Helen.
expensive, I think.
It is. It's, you say it cost about $2,000 to
With the
recharge.
Aramco company before anyone inside that room, that Helen system release alone, just you was there, you take a warning for that.
Yes.
You are responsible about that release of Helen. Almost already released without anyone touch. Very sensitive, that sensor.
Most efficient fire extinguishers, Ali, one of the most efficient fire extinguishers is probably the small powder extinguisher, which they sell even, you can buy them for about 50 reals for your home. Very efficient. If you have a fire, a small fire, like say in a stove or a cooker, just one little squirt of this thing and it goes out like that. Very efficient indeed. Powder, that one is, yeah. Yes. The other type is the carbon dioxide one. Not quite as
CO2
CO2, yes, which is carbon dioxide. I must admit, I think they're going a little bit out of fashion now. I'm not so sure there's a lot of them around. Now, the Class A is water, isn't it? Now, a Class A extinguisher, water extinguisher, is usually, the standard is to put it in a container which is silver coloured or you know, no paint on it. So you recognise it, because water's special. You should only use it under special circumstances, dry fires, nothing to do with electricity, of course. And also, if you have a fire that's caused by spilt gasoline or oil, you shouldn't use water because that could spread it, you know, it splashes it. So you've got to be. That's why the extinguisher for water is usually, you know,
What around
noticeable.
wood and wood and
Yes, if you have what they call a dry fire, a wood or plastic fire where there's no electricity involved and no liquid flammable material, then water will probably be okay. So, but basically that's the sort of question you're going to be asked. You're not even going to be asked the class of extinguisher, just what type in terms of gas or water. Particularly, they want to make sure at this stage that you wouldn't use water on an electrical fire. That's the prime thing.
What is the best for it?
For electrical, well, I mean, if you've got a fire and you know it's an electrical fire, even if you had a halon extinguisher somewhere, you're not going to stand there waiting for it to go off. You're going to pick up a small extinguisher if you can and put it out, aren't you? And the extinguisher you use would be coloured red, and it could contain powder, or it could contain carbon dioxide, depending on the class of extinguisher. If you're in a hurry and you've got to get the fire out quickly, you're not going to sort of read exactly what's written on it. As long as you don't pick up a silver coloured, a water one, then you're pretty safe, no matter what you use. That's what the idea is, anyway.
The handling wasn't found that it would do some corrosion on the components of electronic boards?
Oh, I don't know about that. It might well have been. From what I understand, the reason why it went out of use or is not in favour anymore is its effect on humans. You know, it wasn't as safe as they, pretended it was. The idea was if a halon goes off, you're supposed to get down. Well, I don't think you need to worry about that because you're going to fall down anyway. So, sorry? Yes, it does. It reacts with the oxygen. And that's why I couldn't understand when they were telling us this. When this building was built, it was about, how many years ago? About 12, 13 years ago. They told us that, don't worry, it'll put the fire out, but it's safe. And I thought, well, strange. How can it remove the oxygen for the fire, but still need to breathe? So I wasn't convinced, but I've not heard of anybody sort of being seriously injured with halon. But there we go. They have replaced it with different type of material. It's also very expensive, of course, if it goes off, as you say. The other type of safety thing that we need to concern ourselves with high voltages, and essentially the practical precautions here. First of all, where do you find high voltages in your work as a technician? Where would you find high voltages? Which places would you look for high voltages? Yes, if you were to deal with anything to do with the mains, it's fairly high.
Substation.
Yes, it can be quite high, particularly if you go before the transformer, you can get hundreds of volts. And of course, don't forget, you also get high voltages in these guys, don't you?
You have the screen.
Yes, the EHT for the tube. Transmitter power outputs. Yes, in our case, at the Royal Comms, the HF high power transmitters. Whenever you're dealing with these high voltages, you've got to, well, I know the procedure in Royal used to be you must always work in pairs, 2 of you at a time. One guy goes and does the job, and the other guy stands back. And,
In case of what?
okay. In case he gets the electric job.
No, if that died, the other one complete the job.
The idea being that if the guy gets an electric shock, the other guy can do something about it.
Shut off the
And they should shut off the power, that's the first thing. He's supposed to stand by the switch. And they have blankets and stuff they can throw over to pull them away, and they have big rubber gloves, and they have rubber mats on the floor, thick rubber matting and all sorts of things which you're supposed to wear if somebody did get an electric shock and obviously collapsed, but the power is still there, of course you're going to be very careful. The first thing you should do is switch the power off, isn't it? But imagine a situation, God forbid that this ever happened, where you can see the guy you know, he's still got the electricity connected to him, but you can't find immediately the power switch for some reason, then you've got to try and get the guy off as quickly as possible.
By wood and hit his hand.
Well, you've got, yeah.
So
Obviously, it's no use you going to touch him yourself because you're going to be ended up in the same position. So you've got to use something to push him away. But I don't think that's that's a practical sort of thing you've got to bear in mind. If you're on top of an antenna and somebody suddenly decides to start transmitting while you're up there, you could again get electric shock. But again, it's, the procedure should be that if anybody's going up the antenna to remove the power. And again, there should be another guy responsible down to make sure the power is removed.
Why would they use safety locks?
There should always be safety locks of some sort for most high voltage applications. Like for instance, in a large power transmitter where there's a chance of high voltage, if you open the door, it's supposed to operate a micro switch which will cut off the power so that it's safe. But of course, to service it, you need the power on. So there must be some way of overriding that. And that's when the danger comes. That's when the danger comes, when you override the power. And to measure voltages, instead of using the little probe of the meter, you use a long stick.
Sticks, yeah.
And even then you can get a spark or something that can...
Because there's some different kinds of sticks. Some are used for 11 kV, some are used for 34 kV.
Yes, that's right.
So you can't use this for this.
Yes, you've got to be a bit careful, otherwise you'll burn the stick out.
In Hadid company, in Jubail, they take electricity from two companies, Ski-Q South and Ski-Q West. East and West. They used to take 230 kV from each company. That goes to SF6 breakers, stepping it down through transformers to 34 kV, stepping it more down until it reaches the heater coils, until it reaches about 800 volts, but with 30 kilo amp or 60 kilo amp, 80 kilo amp.
That's a high current.
A high current. The whole building starts to vibrate and the coils go down.
Yes. Well, luckily we don't have anything quite like that here. Thank goodness. But it does sound a bit scary, that. I'm always a little bit hesitant about high voltage stuff.
The 34 kV breakers are something this big.
Yeah. Yes. And when they break, they make a tremendous sound. Yes. I've seen those. It's tremendous. So basically, a lot of this sort of is common sense. It's sort of things you think about, and if you're going to be asked any questions, it'll be quite obvious what the answer should be regarding high voltage. Just take precautions in handling high voltage equipment, anything to do with high voltage. Not all high voltages can kill you in a number of ways, of course. One, it can literally electrocute you by the strength of current that flows through the body. Another is simply the shock. Although it might technically not kill you, just the shock of getting the voltage can cause you to if you have a weak heart, could cause the heart to flutter or stop. And the other, of course, is more of a physical nature. You could be, imagine a metal cabinet with a metal bar, and you're bending down, and you touch something, and you suddenly hit your head, and that can, not the voltage, it's just the sudden shock and hit your head on the bar or something. Yes, well, all this comes under the sort of physical thing. Again, you see, if you're climbing, say, a mast or something, even if it's not very high, it doesn't have to be very high, and there's any chance at all
كان في كل شيء ترى الديسكتوب ما كان
لا أول
صور بسرعة.
أنا أكو يا شفت الثمانية يا شفت السماتو.
comes when the action has been performed. As I say, these map pretty closely with what was seen on the in terms of the services, that you're allowed to send and receive data, open and close files, read and write those files. So that, in essence, is what a file transfer protocol would look like, and that gives you some of the flavor of what the ISO standard is going to look like. That's one of the best examples of an application protocol. I think you'll notice that we've not had to deal with a lot of the issues we saw at the lower layers, things like windows and flow control, error control, retransmission, and so forth. The reason for that is that the session layer and the transport layer are basically taking care of that for us. Transport layer is providing the reliable transmission of data. The session layer is essentially managing the dialogue, and we'll do the checkpointing and the turnaround if it's a half duplex protocol and so forth. So that when you get to the application layer, all those details are gone. And that was the entire point of the OSI model, is that communication is a very complex function, and to try to do it all in one package is an overwhelming task and is bound to lead to programming errors. So what we've done is break it up into 7 layers. The result is that the application layer becomes much more manageable. So I'd like to look at one final set of services that can fit within the OSI environment, basically data retrieval services that allow a user to get access to some public database. And there are 2 versions of this service that have come into some use, text and video text. And we'll first describe the operation of each, and then look at some of the standards implications and protocol implications. This is a typical example of how teletext works. You have someplace an information provider, and this provider has a set of data that is organized into pages. It might be lists of phone numbers or prices of items in a retail store, schedules for theaters and concerts and so forth, information about stock market, and any information that can be provided that is of public interest, news items. What is done is this data is organized into a circular buffer of pages, generally a smallish number of pages in the few hundreds. These pages are then broadcast over the television broadcast facility. And there's a technique that's used to, in effect, embed this data within the TV signal in such a way that when the receiver receives a TV signal, if you're just tuning to a channel, the user will see the ordinary program that was meant to be seen. But embedded in that signal, encoded in it, are these pages of data, and it's possible to essentially filter them out and discard the video picture, the actual television channel picture, and instead display this page of data. So you can either display the ordinary programming from the television system or the page of data. And we have here a decoder which is receiving these pages, and they're coming in a circular fashion, that is, they repeat. And this system will buffer them as they come in, and then the user can have a keypad associated with this decoder, can indicate that the user wants to view data, and indicate which page of data is to be viewed, and that page will be displayed on the television set. So notice that this is not a two-way interaction between the user and the information provider. It's all one way. The information provider provides these pages of data. It appears to the user as though it's two-way because the user is selecting a particular page and that page comes up on the screen. So that's a very simple system. Requires very little equipment at the user site, but it's obviously very limited. It's limited to the number of pages that you can encode and embed into the TV signal. And as I said, this is limited to just a few hundred pages. So what is a more powerful system and what is beginning to become more prevalent is known as video text. And this is a two-way system. And what we have here, again, is an information provider. This provider may now have a number of databases. And the databases are not simply static information like stock market prices, although they could be that, but they could also be databases that can be updated. For example, a user might be able to actually purchase items off of a catalog and have that item charged against the user's account. So now we have to have interaction between the database and the user. And at the database end there is a computer that manages this video text system. The user, generally through the public telephone network, establishes a link with this computer and basically dials up that computer. And there are special video text terminals, or actually a personal computer or other kind of terminal could also be used. Any sort of terminal that can be adapted for this system. And the user has a keyboard and can sit at the terminal and basically interact with the system. It's also possible to do this on the user's TV set with a keypad and some adapting electronics so that the data that's being displayed shows up on the screen. So either with a television set and an attached device or with a terminal or personal computer, the user can interact with the system. So those are two services for public information provision. Now let's see how we can relate that to standards and protocols and the OSI model. Basically, what are the areas that one might want to standardize in such a scheme? Well, for video text, you might want to standardize that user terminal dialogue. It would be nice if there was a simple, structured dialogue that the user could use to access data. And what we would like is the same dialogue to be standardized across all systems, so the user does not have to learn a new dialogue every time a different system is used. Between the terminal and the system itself, you need a protocol to support this dialogue. And again, that is something that's amenable to standardization. The database, you might want to specify the format of the database so that different systems can cooperate together. And finally, the data that's coming back to the user's screen has to be displayed in some fashion. And so you might want to standardize that. In fact, what's happened is that most of the emphasis has been on this latter category, the display techniques. Very little work has been done in the first three areas, although that should come with time. So basically, we're dealing with the display techniques. This is essentially a presentation level sort of protocol. The others, the user terminal dialogue, you're getting more into the application layer, but the display is actually a presentation level sort of protocol. And some work has been done. Unfortunately, some competing work, several organizations have gotten into the act of trying to standardize this. And I'd like to just briefly give you an idea of what's coming out of this standards work. First, an ordinary screen on a terminal or television is capable of displaying characters. Normally, something like an 8x10 grid would be used. That is, if you have a terminal screen and it can either illuminate or not illuminate individual dots, you would use a matrix of 8x10, and within that matrix you could define all the letters of the alphabet and digits and other sorts of characters. So that is something that any system will have. It'll allow you to display textual data. The standard called Alpha Mosaic not only has this, but also has what's known as a 2x3 grid, and each of these, which occupies the same space as the 8x10 character. So in effect, what you've taken is, you've taken these grid patterns and you're blocking them up into larger patterns. And each of these larger areas can either be black or white. So now what you're getting are are rather large, crude visual patterns. But if you concatenate them, you can build up images, pictures of things, so that instead of just characters, instead of just text and numbers, you could display some rather unrefined or rough images. You're certainly not going to get a very high level of contrast, but you get a crude graphics capability. So now you have not only text and numbers, but you also have graphics. Now that still is going to be a relatively inexpensive system because with the 2x3 pattern, the electronics for doing that is fairly simple. And that has been developed primarily in Europe. In the United States, there's been some work on a more elaborate system known as alpha geometric. And basically what this allows is it allows the 8x10 characters that we saw before. It allows these 2x3 patterns, but in addition, it allows you to literally draw pictures to define points with lines or arcs between them. So now what we have is a very complicated standard because you're allowed to define and draw images. From the user point of view, this is much better because now you can get virtually any image can be drawn on the screen, only limited by the resolution of the screen itself. The reason for the competing standards is that the more complex standard, while it's better for the user, requires more complex electronics and more complex software. And so organizations are essentially working on both of these forms of standards for video text and teletext because the same presentation can be used on either since they're both using the same kind of screen. So that very briefly is a look at the presentation level standard for video text and teletext. And what we've done is in this session looked at a few examples of these higher layer protocols. And what we're going to see in the next few years is a proliferation of these, things like electronic mail, document architectures, document transfer architectures, job entry, and so forth. And what there will be is a family of protocols at the application and presentation layers, all using the fundamental services of the lower layers of the model. And again, it seems as though the work that has been done by the ISO committee is bearing fruit in the sense that it has become clear that one needs to break these functions up into layers in order to make them manageable. And also it has succeeded in the sense that now that things are broken up into layers, it's much easier to focus on a layer and develop a standard, and that in fact is what is being done. Thank you.